First of all, I would like to thank the organizer for organizing this conference. The second thing, I would like to thank the lecturers, that three of them are my collaborators, and our papers were really very well known, papers that we are written together. Anton was not my collaborator, but I hope that I will have the possibility to collaborate with him, maybe even in the next days. So what I was doing recently is I studied, I suggested a geometric approach to quantum theory. I will explain a little bit more about this in a moment. However, I will formulate something about the stuff. But I do not want to talk about geometric approach at length, because the goal of my talk is much more concrete. It is the study of the object that I introduced also recently, which I call inclusive scattering matrix. And I will talk about another stuff that I invented long ago that really is very closely related to geometric approach. This is what I call formalism of L functionals. So that I will try to convince that this stuff is really important, not only when you are trying to study general questions of quantum theory, but it is really useful in concrete calculations. So one of these concrete calculations will be presented. So, but first of all, several remarks about geometric approach that I promised not to talk about it at length, but still I would like to say something. I think that is also interesting. So really, physicists usually work in Hilbert spaces, and this is not always good. Because you cannot live in one Hilbert space studying even a well-defined theory. So I think that the most powerful of approaches that are used now in physics is algebraic approach. In algebraic approach, you start with star algebra. Star algebra is unital associative algebra with involution. And after that, you define positive functionals that satisfy the equation that there are linear functionals on the algebra that are non-negative on elements of the form A star multiplied by A. The form of a convex cone that I will denote by C. But usually you can consider normalized states when you have an additional condition that omega linear functional, omega applied to 1 to unit element algebra gives 1. So when you have representations of this algebra A in Hilbert spaces, then every element in Hilbert space, or even every density matrix in Hilbert space, they define such a functional. So this is really related to Hilbert space formulation. However, there are many representations of algebra, of star algebra, and when you have infinite number of degrees of freedom, there are non-equivalent representations. There are many Hilbert spaces that you should consider. It is difficult to single out the Hilbert space that you really need. So therefore, algebraic approach is really much more powerful than approach based on Hilbert spaces. But the geometric approach that was suggested in my papers is even more powerful. Really, in a geometric approach, I am taking a starting point, a convex set of states, or a cone of states. And this is, and all motions are defined in terms of this stuff. So really, you can, in the algebraic approach, symmetries and evolution operators are automorphisms of algebra. In geometric approach, evolution operators are automorphism of this set of convex set or of cone. And what is really interesting, then in these terms you can define, you can prove some theorems, and you can find what the origin of probabilities. So really, there is something called the coherence, which is more or less equivalent to stuff that in old Copenhagen formulation was called collapse of wave functions. The coherence can be proved under very mild conditions in this geometric approach. If you impose adiabatic random perturbation on your theory, and if you have the coherence, you can say that you can define probabilities. In the case of standard quantum mechanics, you have standard rules of probabilities. That is not the stuff that I would like to discuss today. There is one more thing that is interesting in geometric approach. Really can formulate this in more standard situation also, in standard approach also. Namely, one can consider classical theories saying that not all of observables can be really observed. So really, let us consider, let us think that our devices can measure only a part of observables. And then you can get a geometric theory and geometric approach. In particular, you get the standard quantum mechanics. It is also can be obtained as something coming from classical theory, this restricted set of observables. So that's I think that this is an interesting statement, but again, I will not talk about this, a very simple proof of the statement today.
Can I ask a question?
So, yeah.
Is this about simultaneous measurement, or when you say measurement?
No. This is the measurement theory. It doesn't appear in my considerations. Really, this what I do not consider is interaction of physical system with observer. Nothing of the.
Can I ask you one question?
Yeah.
Which is when you say our devices only allow us to measure part of observables.
Yeah.
There is a mathematical notion which seems to fit extremely well with that, which is not algebra, which is called operator systems, which has been extremely developed, and in which the only thing you require is that if you have two, you have their sum. So I presume that when you say allow us to measure only a part of observables, you can assume that if you have two, you can add them.
Yeah.
But you cannot, of course, multiply.
But you can take commutators.
Can take commutator.
So this is in. I'm starting with usual classical mechanics. This is no operator algebra.
I understand, but,
so this is,
but there is a notion which is very well developed, which is called operator systems.
So I think that yes, probably completely right, but this is something that doesn't require any. My statement doesn't require anything. It's the simple statement that if you take it, probably I can. So I don't want to explain this today in details, but I would be happy to explain this to you, or after the talk, you can repeat your question, that I will explain everything more concretely. That's easy. Okay. So it's one more thing is this geometric approach is that if you have not only evolution operator but also translation operator, then you can do everything that can be done in quantum field theory. This, in a sense, this is quantum theory without fields, without locality, without Lorentz invariance. But you still can define a notion of particle. You can define this particle is an elementary excitation of ground state. You can define a notion of quasi-particle, which is elementary excitation of any translation invariant states. And you can define a notion of inclusive scattering matrix. But you cannot define a notion of standard scattering matrix. And but inclusive scattering matrix is, I believe that is interesting without reference to geometric approach. And this will be the main object that I will consider in this talk. But first of all, I would like to explain, I will not give a definition of inclusive scattering matrix. At the end of the talk, it will be done I will give one of possible definitions, not the best one. Again, I can explain this in questions. But first of all, I would like to explain what is inclusive cross-section. This is standard notion, and it goes as follows. Usually, what you are doing in experiment, you collide two particles. You can collide three particles, but usually you collide two. And then you look, usually you look probabilities that appear some other particles with some momenta, and you consider corresponding density of probabilities, probability density. However, usually in experiment, you have really a possibility to measure several particles, but usually you do not see something that appears in this process. So really, you can consider a process where you have some data plus something. And then the corresponding probability density, when you really integrate over the something, it is called inclusive cross-section. So it is really the notion that is used all the time in physics. However, the usual scattering matrix doesn't give it. You can give scattering amplitudes, and you can take this square, modulus square of this stuff, and you will get this usual cross-section. But what I introduced is something else. This is inclusive scattering matrix that is closely related to inclusive cross-sections. But you should not take any squares, simply you should take some limits and you will get inclusive cross-section.
So excuse me, so this green function, you take it as like in the quantum field theory as particles are like point particles are zero-dimensional, but what happens if you consider it as like a string, a one-dimensional object? Can you replace this green function by something which can describe this?
Yeah, so really, so probably in longer talk I could give a definition of particle that I'm using, and I'm ready to explain it after the questions. However, let me go ahead at this moment. Usual scattering matrix can be expressed in terms of green functions on shell. This is what is called Lemon-Simanchik-Zimmermann formula. The statement is, this one of the main statements that I would like to emphasize, is that inclusive scattering matrix can be expressed in terms of generalized green functions on shell. This is an analog of LSZ formula. And I will explain what is a generalized green functions are in the next slide. For this generalized green functions, you have diagrams, and so you can have some analog of Feynman diagrams. And so this means that inclusive cross-sections can be calculated as easy as usual cross-section, as usual scattering matrix. And very recently, this notion of inclusive scattering matrix under different name was rediscovered in the paper that is mentioned here on this slide. Now I would like to fulfill my promise to say what is a generalized green function. Usual green function is defined as you take chronological project of some operators. So this is product. You have product of operators which depend on space and time variables. So that you say that times are decreasing. It's called this. When you take expectation value of this stuff, it is called green function. But you can also consider anti-chronological project where the times are increasing. And when you take expectation value of a product of chronological product and anti-chronological product, this by definition generalized green function. This generalized green function, they appear naturally in Keldysh formalism of non-equilibrium statistical physics. They also appear in formalism of L functionals that I will talk about later.
Is this what is also called out-of-time order correlators?
Sorry?
Is this also called out-of-time order correlators?
No. You have. Sorry, I didn't get the question. What do you get here? You have chronological product of some operators. Then you take chronological products, anti-chronological product of other operators. You multiply them, and you take expectation value. This is. So now what I would like to say that now I would like to try to convince you that inclusive scattering matrix is a good object. First of all, it carries precisely the same information as conventional scattering matrix, not less, not more. However, this is true only in the case when the conventional scattering matrix does exist. And it's conventional scattering matrix cease to exist in many cases. For example, if you consider not particles but quasi-particles, conventional scattering matrix doesn't make it any sense even if you consider scattering of almost stable quasi-particles. In quantum electrodynamics, conventional scattering matrix is not defined. Basically, every process involving fixed number of particles has zero probability in quantum electrodynamics, because in every process you have emission, in every real process you have emission of soft photons, photons having very small energy. So generally, scattering matrix does exist in cases when the theory has particle interpretation, what is called. This means that every state decays into particles by time tends to infinity. But nobody knows that this is true in non-relativistic quantum mechanics, but nobody knows that it's true in relativistic quantum mechanics, and nobody knows, for example, that dark matter really consists of particles. Even nobody knows what is dark matter at all. So it is possible that in these cases, inclusive scattering matrix is not only useful but also necessary.
Albert, you didn't define what is including scattering matrix. Can we know?
I can define this in several ways, and in one of ways it will be defined at the end of the talk. And after the talk, I can really.
To understand what you say, we need to have some definition of inclusion.
So let me go ahead. Right now, I'm limited in time. So I cannot. Everything can be explained, but it takes time. Okay, so now I will go to one of ways to define this. Inclusive scattering matrix, and this way is not the best way, I would like to say, but I would like to use this possibility to talk about the stuff that I invented many years ago. Really, this was my first physical paper. So I believe this was 1967. And after that I shifted to other stuff. This paper was more or less forgotten. However, it was the stuff was not this stuff, but equivalent stuff. In much less transparent form, was invented by Umezawa under the name thermofield dynamics, and used in non-equilibrium statistical physics. But I will go now to the stuff that was invented long ago. So first, I'm trying to quantize a classical theory. So I have standard Poisson brackets. I will write this so usually in usual quantum mechanics you write, you quantize them, you get canonical commutation relations, CCR, but P and Q are self-adjoint operators, but it is better to work with operators of the form P plus minus IQ, and then you get another, the same CCR, but written in different form. So basically, this is another possibility to write CCR is in the last line of this slide. It's very, very well known representation of CCR. So you have these operators A of F and A plus F that are usually called annihilation and creation operators. And this is because you consider what is called Fock space, Fock representation of canonical commutation relations, where there exists a cyclic vector theta that vanishes after application of annihilation operators. This is the standard Fock representation that physicists usually use. Even they use this representation, Fock representation. But there are many other representations, and you cannot really restrict yourself to Fock representations. You should consider all of them. Because, for example, in statistical physics, if you consider various equilibrium states, that every equilibrium state defines its own representation of CCR, and these representations are not equivalent.
So this theta here is the ground state, represent the ground state. The theta represent ground state.
What is theta? Theta here is Fock vacuum.
Vacuum.
This is so now there is a simple idea. First of all, we introduce operators W, F, with the formula which is written here. This exponent, some exponent of creation operators, and multiplied by exponent of annihilation operators.
What is the meaning of the plus?
You can say, you can read it as star.
Oh, star, okay.
Yes, this is creation. I write this plus with dagger, if you would like. So, what I'm doing for every density matrix is you can consider instead of density matrix, you consider simply vectors of Hilbert space. Then it defines some. So every vector defines of some density matrix, and all density matrices are mixtures of these density matrices corresponding to pure states. So I define for every vector and Hilbert in any representation of my CCR, or for every density matrix in any representation of CCR, I define this functional that is written here as trace of product of W, F, and density matrix. And what is important to say, that this functional is well defined for any density matrix in any representation of CCR. And this is a simple fact, because my operator WF is really a unitary operator up to some constant factor. So this trace that's written here always exists.
You mean it is very close to taking the exponential of a hat of f bar minus a hat of a plus of f? Yes.
Yeah.
It's the exponential of a pure joint operator, so it will be unitary.
Okay. So what can I say? That this functional really gathers together all states in my quantum theory, because earlier I have a lot of Hilbert, a lot of representation, a lot of Hilbert spaces, vectors there, and all of them were candidates for the description of state of my system. But now I get a functional that gathers all of them. And therefore it is much better object than vector of Hilbert space or symmetrics there. So I consider this functional. I will write them. It doesn't depend holomorphically of f, and therefore I will write this functional as functional of f bar f, as physicists usually do. So I define this stuff in absolutely pedestrian way, but in reality you can define this in an algebraic approach, again in a very simple way. You can consider what is called Weil algebra. And while algebra is usually is understood as algebra generated by creation relation operators satisfying CCR. However, it is better for me to work with exponential form of Weil algebra. It's not quite equivalent. This is the algebra consists of operators in Fock space that contains all these operators WF that I introduced. And it's closed in non-topology. And then you can work in algebraic approach, and then this you can represent states as linear functions in this algebra. And simple remark is that linear functions on Weil algebra in exponential form can be represented as nonlinear algebras on generators. That's it. But this is in a sense, this is an important step, because this nonlinear functionals is really an object that's easy to operate with. So, and then what I'm saying, that I will forget everything that I started with, and I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of motion for my functional L. It has the form of evolution equation. And then I will consider equations of the derivative with respect to time is h applied to L, where h is some operator that I call a Hamiltonian quotation marks. And if I had a theory, classical theory, it has some formal it has some Hamiltonian. This Hamiltonian is a formal expression from the viewpoint of operators in Fock space. It is nothing that you can consider as a mathematician. However, you can go from this formal expression to some expression that acts on L. It is easy to calculate. And this expression for this operator that I on space of L functionals, in many cases, is well defined, even in the case when the original formal Hamiltonian wasn't defined. In particular, if you have translation invariant theory, where you have this your ground state doesn't coincide with Fock vacuum, then this Hamiltonian never is defined, and this Hamiltonian quotation marks is well defined in at least in the framework of perturbation theory. In all cases, when you do not have infrared ultraviolet divergences.
But excuse me, just one question to get again this into this L functionals take positive real values?
Depends on depends what do you consider. In this formula, this is what is L functional. You have physical L functionals, and you have functionals that appear in this formula that you have in this formula. The formula for the functionals in this formula are complex valued, and so this. But still, this positive functionals. They are invariant with respect to this flow, to this evolution operator. So what I will do now, again, my goal today is to explain simple things that show that you can calculate with these L functionals, because L functionals is, in a sense, it is something that is very natural in geometric approach. You are working with these states instead of working with vectors in Hilbert spaces. So what I will do right now, I will consider quantum electrodynamics, but not as but with some restrictions. Namely, I will neglect the action of photons on electrons. So, and then I have really a Hamiltonian of this system, which is a sum of three Hamiltonians of photons, and interaction. But interaction I consider this current. usually this is the standard formula. The formula which written here is the standard formula for interaction. But usually J is considered as psi bar gamma mu psi, which is an operator. But because I neglect the action of photon by electrons, I consider this J simply as numerical function. This so what I will do further. So this is the stuff that I consider in Hilbert spaces. I would like to consider this in Fock space, but in Fock space I do not have vectors that are correspond to my physics. So basically, if you have an electron, this electron is dressed by a cloud of photons. And there are many of these photons. And this cloud does not lie in Fock space. You should go to, you should either use non-separable Hilbert space, or you should consider some other space. But anyway, you do not have in Hilbert space. You do not have this states that we need. And therefore, this is a question with what is called infrared problem in quantum electrodynamics. But let me look what happens further. Now, I will write down the equation of the equation for L functionals. They are written right here. This is easy to derive. This is a complete algorithmic, simple algorithm to write this. After that, I am saying that these equations of motion can be solved very easily. You can go what is called in physics interaction picture. Then the equations will be really easily solvable. So really you have this equation on the last line of the slide. And here this operators depending on time commute with each other, so that's really it's very easy. It's easy to solve this equation. But even if you have a linear expression that with non-commuting operators commuting on a constant, also can solve this equation. So that's. But basically, you're solving these equations at the moment. You simply write down this equation, the form that the solution, and the form exponent of something, and you have expression for evolution of L function in a moment. So you can rewrite this. Solution in a little bit different form. That's simply to recover this physical sense of this formulas that.
What is epsilon of k?
This epsilon of k is, I believe this it is defined here. This is absolute value of this is simply absolute value of k in this case. Okay, so And now, when you solve this equation, you can calculate the inclusive cross-section. For inclusive cross-section, simply you should calculate the number of particles that go in some direction without looking at other particles. And you get a formula. This is a quantum formula, but really here, this is here in some sense, this quantum formula is coincides with classical. It coincides with classical formula in a sense. But again, you have this. To get this in standard formalism, you should sum a geometric progression. But here you don't need this. You have calculation is much easier. Yes, you have the inclusive cross-section and photons. You have a similar formula. This is a simplified version of electrodynamics. You can consider full electrodynamics, you can consider L functionals. And so that's basically what you will see, that inclusive scattering matrix is finite, and really inclusive cross-sections are finite. The fact that inclusive cross-sections are finite is well known, but usually this fact is obtained as a cancellation of infrared divergences. You get a divergent answer, but you have cancellation. It seems that in the case of when you study the stuff in terms of L functionals, you will have, you see that in my example, these divergences simply did not appear. They did not cancel, they did not appear. And it seems that the same stuff, the same statement is true in general situation. So, but now I would like to say that how you can define this inclusive scattering matrix in the formalism of L functionals. So you should consider adiabatic scattering matrix. So this adiabatic scattering matrix, you consider Hamiltonian, which is represented as sum of free Hamiltonian H0 with interaction Hamiltonian V. And you multiply this interaction Hamiltonian by some function that changes slowly, adiabatically. So then you consider this evolution operator with this interaction picture. This is called adiabatic scattering matrix. And if you can, but you can do this either in standard formalism or in the formalism of L functionals. So, in standard formalism, really to define any evolution operator, you should go to finite volume. You should make infrared cutoff. So this is, and then you can define this adiabatic scattering matrix, and you can prove that scattering matrix, full scattering matrix, it is renormalized scattering matrix. I would like to stress that when I say scattering matrix, it is always renormalized in the sense that I take into account renormalization of mass, of self-energy, better to say, and the renormalization of wave function. They are taken into account, but not renormalization of charge.
Excuse me, what do you mean by A goes to 0? What?
A is adiabatic parameter. So really look here what is written here, h of AC. When A tends to 0, you have slow.
You have K of K creation and operation denoted by the same letter.
Sorry?
No, the creation and operations denoted by the same A of K. Yeah, it was confusing.
Yeah. That's sorry. Yes. So, okay. This is the formula for this renormalized scattering matrix in terms of adiabatic scattering matrix. I would like to stress that usually the people in many books, scattering matrix is defined as a limit of adiabatic scattering matrix. But what is written in all books gives not scattering matrix that is not renormalized. This is only first step. But here you have renormalized scattering matrix. But you can do the same stuff for really for L functionals. And the statement is that then you will have inclusive scattering matrix. This is one of possible definitions of inclusive scattering matrix.
Don't you have a star missing for one of the UA?
Sorry?
You don't have a star missing?
Where's star? No stars.
So it's UA, SA times UA.
Yeah. No stars.
Not conjugation.
No conjugation. It's surprising, but no conjugation.
No inverse.
Yeah. Okay. So this is the definition of inverse scattering matrix, and this is my last slide. So really, in this from this consideration, I can really say what is the relation between inclusive scattering matrix and conventional scattering matrix. Really, and this relation is written right here. So basically, what do you have? You have usual scattering matrix. It acts in Fock space, and but then this inclusion scattering matrix that acts in Fock space really gives a natural action on density matrices in Fock space, and then you can go to L functionals, and you will get inclusive scattering matrix acting on L functionals.
So again, you apply S hat twice.
No. Here you have here I have star, of course. Here I have star.
I'm confused. Why do you not have the star in the previous?
So I also was surprised, but really you do. you do not need star there. So that's surprising, but that's the fact. But it's really, this is not a unitary transformation. You should really.
It looks like
No, this is so.
basically, when it's acting on one, it doesn't.
Yeah, so really, basically, there is another formulation of all this stuff that I can say that really, what do you have in that in my definition, not really in any definition of scattering matrix. Scattering matrix is not really well defined. It is defined up to some ambiguity, which so really you. If you would like, I can explain at this moment what does it mean a particle in this approach, and then it will be clear that scattering matrix is not defined uniquely. It is defined up to some equivalence, and so that's this representation that I have here. By the way, you see that there is no volume here because L functions are simpler. You shouldn't take volume cut off to define evolution of L functionals. What is important to say that you can give another definition of this scattering matrix or inclusive scattering matrix in the following way. You have some equivalence of scattering matrices. And so then the definition is as follows, that scattering matrix or inclusive scattering matrix is a limit of adiabatic scattering matrices in some equivalence class, the same equivalence class. So really you should not, with this multiplication by this U, doesn't change the equivalence class of scattering matrix. So that's in a sense. Yeah.
Here in the definition of inclusive scattering matrices, you don't divide by the volume.
No, I don't. No. You don't need this. This in the first formula, so you see that there was something. This you needed this denominator, but in L functions you don't need it. You don't need volume at all. You can work in infinite volume from the very beginning.
Okay, thanks.
Okay.
Some questions, but maybe more questions. Actually, I have some little question.
Yeah.
In the generalized green functions, you first have it's put on the time which will decreasing and then increasing. Yeah.
Sorry.
In generalized green functions.
Yeah.
You have put operators for times first decreasing and then increasing. Yeah. Something like this.
So you can put
in this order, yeah.
You can put. I consider here real times.
Real times, yeah, real times.
But simply real times.
Yeah, but when you put operations, the times I remember was first decreasing and then increasing. Yeah.
Yeah.
Yeah. Is it related to fact that you, in this L functionals you take creation and regulation first creation is an annihilation operator.
No. It is related. So I can explain what is the origin of this stuff for L functionals. Why L functionals lead to these green functions? The explanation is very simple. For L functions, you need only ordinary chronological product. Why? Because for if you have operator elements of algebra, so L functional are functionals, linear functionals on algebra,
Non-linear.
Linear, and then there are linear functions that are represented by non-linear functions. There are linear functions on algebra, and if you have an element of the algebra, it acts on linear functionals in two ways. You can multiply from the left, and you can multiply from the right. You can multiply argument from the left or from the right. So you have operator that I denote by A and A tilde. And now, because you multiply somewhere from the right, this changes the order at your anti-chronological product becomes chronological. And therefore, really what do you have is that when you define green function and the formalism of L functionals, you need only chronological products. And therefore, you really can develop in standard way, you can develop perturbation theory, and so on.
Okay, sure.
Yeah, so Albert, so if I understand what you are saying is that if you sort of freeze the electrons so that they only manifest through their current, okay.
Not free.
Sure. But what I am saying, what I have understood from what you say is that if one would try to work in Fock space, this is wrong because the representation is changing with time. But if you work with the L functionals, then everything is fine.
Okay. Precisely.
Okay.
Precisely.
Okay, fine.
And this is
I understand.
really the explanation why L functions are better than vectors of space. So that's,
Okay, so let's thank the speaker again.